Now, the next step is going to be using the design equation to find the minimum required diameter or diameters for the various points. The sizing the diameters is going to be mainly based on the forces we're going to have at these points. So you can see from the geometry of the shaft is that we're going to have small diameters and large diameters, and it's not only going to be about having the shape or the diameters to be that way, because I can simply use the same diameter shaft. I mean, it's going to start the same diameter from the beginning till the end, which is going to be the maximum value again to have for the diameters according to the maximum force we're going to have for this section. But the thing is, we need to reduce the size of different sections to reduce the weight of the shaft in general, because I don't want to have the weight of the shaft to be a problematic we have for the total design for the machinery we are going to make. In addition, the different section can provide the shoulders for the different components. As you can see here, that the first section, if we're going to start from the D1, is going to be smaller than the one later. So we can have the keyway to hold the gear A in position, but the shoulder is going to prevent it from shifting to the right. Same thing will happen to the bearing. We are going to have at the point D6, and the gear we have in D5, and the bearing we're going to have in the D3. And that's what we're going to actually go through in the next calculation steps. The load, shear, and the moment diagrams will help a lot to identify and calculate the forces we have in different sections, which mainly again to work on the section A, B, C, and D, with some assumptions about the distance between them and the types of the fillet radii we're going to have for these different sections. The main equation to determine the minimum required diameter for various points is going to be the equation we have in the textbook. And this will take in consideration the N, which is the design factor, the KT, which is the design factor as well, and we have the M, which is the bending moment at this point, the Sn prime, the value for the T, which is the torque, the Sy, which is the yield stress. Okay, so you will remember that some of the section does have torque, others doesn't. And that's what we're going to consider in our design in this next step. So we start with the point A. The gear produces a torsion in the shaft from A to the right. To the left of the A, where is a planing ring, there is no forces, moment, or torques. The moment at A is equal to 0 because it's going to be free ends of the shaft. Thus, the equation we are going to use will simply going to reduce to the following. No moment, but I do have a torque. So I will shorten the equation above to a new version of it. And then I will start to add the parameters. So the torque, as you remember, has been calculated, and we can simply just add to the equation to be 2388.5. Divide that by the value for the SY we found, which was 572.3 megapascal. Square this ratio, multiply by 3, divide by 4, put it on the square root, multiply by 32, which is a constant number, multiply by the n, which is the design factor that we had, and divide by pi, and then the whole thing will be under square root of, it's going to go under the root of 0.33. And we get the value to be equal to 40 millimeters. Point B, the location of the bearing with a sharp fillet to the right of the B and well-rounded fillet to the left. It is desirable to make the D2 at least slightly smaller than the D3 at the bearing seat to permit the bearing to be slid easily into the shaft up to the place where it's going to be pressed to its final position. There is usually a light press fit between the bearing bore and the shaft seat. So to the left of the B, I'm going to decide that the diameter 2 is going to be calculated where the torque is equal to 2388.5 Newton meter With the KT I'm going to use is going to be 1.5 for the well-rounded fillet. So the bending moment is going to be the calculated from the bending moment diagram for both planes, the vertical and the horizontal, and again find the value for the magnitude. And thus is going to be equal to 2541.8 Newton meter. From there, again to apply to the equation of the diameter, and I find diameter 2 is going to be 76.5 millimeters. To the right of the B, for diameter 3, it's going to be a little bit larger. So the torque is going to be the same. The KT is in that case going to be 2.5 for the sharp fillet instead of using the rounded fillet. And I'm going to use the bending moment diagram to find the bending moments, and it's going to be the same. Then I'm going to use the equation now, and the KT value will still going to increase the diameter to be 90.43 instead of 76. Now the D4 will be larger than the D3 in order to provide a shoulder for the bearing. Therefore, it's going to be safe. So the point C is going to be location for the gear C with a well-rounded fillet to the left. A profile key seat is going to be for the gear, and the retaining ring groove to the right. The use of the well-rounded fillet at this point is going to be actually a design decision that requires that the design of the bore of the gear accommodate the large fillets. Usually, this means that the chamfer is going to be produced at the end of the bore. So to the left of the C, which is going to be diameter 5, we're going to find the torque, and the KT value is going to be used for the profile's key seats to be equal to 2. So the bending moment at C is going to be once again the magnitude of the horizontal and the vertical plane bending moments, and it's going to be equal to 2091.5. So obviously I can tell that the KT is going to be smaller, the torque is going to be the same, the bending moment is going to be less, so I will expect that the diameter for this section is going to be smaller than the previous one, and it's going to be dropped down to 78.83 millimeters. Now, once again, just remember that these diameters are going to be the minimum diameters I can use. And once again, we can choose the diameter based on the catalogs for the different parts we have. The right of the C or the D5, now the torque is going to be 0 because we gave all the torque away at the point C. The KT is going to be equal to 3 because we have ring grooves. Now, the bending moment can be calculated, which is going to be equal to 2091.5 Newton meter. And then the diameter will exclude the equation for the torque, and we're going to get the diameter to be equal to 89.9 millimeters. Now, we start to apply the ring groove with a factor of 1.06, which raises the diameter D5 to 95.3 millimeters to the right of the C instead of the 89.1 millimeters. Point D at the end of the shaft to the right. The point D is the seat for the bearing D, and there is no torque or bending moment in here. So, however, there are vertical shearing force equal to the reaction of the bearing. I cannot consider the diameter there is going to be 0 because I need to fit my bearing in. So we are going to use the equation that the VD is equal to the moment, the shear forces we are going to have in both the X plane and the Y plane. So I can find the magnitude, and it's going to be equal to 8,234.1 Newton. The KT is going to be 2.5 for the sharp fillet, and the equation we are going to use is the other equation we have in the slides that consider the shear force instead of the bending and the torque. So applying this equation, we will find that the diameter there, the minimum diameter is going to be 18.55 millimeters. Now we did calculate all the diameters, and we are going to go from there to summarize everything. So in reality, diameter at D will probably be made much larger than the 18.55. And this will be because the size of the reasonable bearing strength in these points definitely is going to be larger.